Misha, somehow we no longer, at least I no longer see your slide. Is it normal?
Yeah, I think they were.
We just stopped sharing.
Yeah, our master temporarily suspended.
Ah, okay.
So I think, Anton, just before we begin, I think there was a brief announcement that Thomas Strebel wanted to say. Thomas, would you like to?
So wait. But maybe is it so urgent or?
Yeah. So there's a good there's a good news which we wanted to share with the community, and it starts with the fact that the Erwin Schrödinger Institute in Vienna is starting from this year giving a medal for outstanding contributions in mathematics and physics. And I was almost officially asked to announce the winner of this year. So the winner is Anton Yurievich Alexeyev. So please applaud with me for him. Congratulations, Anton, and you really deserve it.
Thank you very much. Thank you for nice words and for announcement, Thomas. And actually, it was, I think, Thomas and Chen Chang who nominated me. So thank you again for that. But I think right today we should probably focus on the speaker and on the talk and not on the chairman. So let's go back to the plan. Thank you again. I'm very touched. Can we share the screen with Misha's slides?
Should I do that, or you can?
Yes.
Okay. Right. Where is it? Oh. Okay. Let's do it again. And yeah.
Okay, so today it's a pleasure to have Misha Gekhtman at Global Poisson, and he will be speaking on generalized cluster structures related to the Drinfeld double of GLN. So I give you the floor.
Thank you. So thank you for the invitation. And well, I didn't expect this to be on such an important day, so I feel certain trepidation, but I will try to get over it. So this is a joint work, ongoing work with Misha Shapiro and Alec Weinstein. I'm going to, given the nature of the seminar, to emphasize Poisson side of things, but sometimes I'll have to go into more combinatorial direction. And Anton instructed me to start slow, which means that I will probably not get to the end, but that's okay. This talk is based on these 3 references that will be available to everyone when I share the slides. And I want to start with just this description on what do we mean by cluster structures and Poisson varieties. So I want to talk about cluster structures rather than cluster algebras today. And well, cluster algebras are now 20 years old, and the theory founded by Fomin and Zelevinsky with a view to dual canonical basis, a study of total positivity, now has many applications, but I want to focus on maybe more utilitarian side of things. So again, this is a Poisson seminar, so let's just talk about Poisson varieties. Suppose we have a nice Poisson variety, and we also wanted to admit a certain toric action. I will explain this later. And whenever you deal with Poisson brackets, you usually prefer to find coordinates in which they look as simple as possible. And so that is what we're going to try to do. So suppose we want to construct a family of coordinate systems that we will call clusters pretty soon, such that, first of all the coordinate functions in each of these charts are regular functions on our variety, and we also want them to be homogeneous with respect to the storic action. And we want every this coordinate system to be compatible with a Poisson bracket. Also, this is called log canonical, diagonal quadratic, and well, at any rate, this is what it means, that the Poisson bracket of any two of these functions is just their product times a certain constant that can be integer or can be can be made integer, right? Because we can scale it if it's rational, so at least rational. Okay, but we're not content with just having one such chart. We want to have a lot of them, and we want any of these two charts. So let's be greedy that we want more good properties. We want to be connected via polynomial transformation in both directions, Laurent polynomial transformations in both directions. Right, so it seems like a very strict requirement, but well, we'll see examples where this actually works. And then we want any regular function in our variety to be representable as a Laurent polynomial in terms of every of these coordinate systems. So extremely nice family of coordinate system. Why would you want something like that? Well, in particular, when you study integrable systems, this is very convenient. And in fact, you can uncover some integrable systems, in particular discrete integrable systems this way, such as pentagram maps and their generalizations. So I'm going to follow an example of last week's speaker, of Chantiang, who started with just a 2x2 case, right? He started with SL2. I will start with GL2 just to show how this could work. So here's my first example. So let's just consider 2x2 matrices with so-called standard Poisson-Lie brackets. I'm not going to delve deeply into Poisson-Lie theory, so especially not in front of this audience, but all this means is that the multiplication map is a Poisson map. But we can be fairly explicit right now and just say that we have a set of 2x2 matrices with this Poisson brackets, which are written down explicitly. And as you can see, so I have to write, well, 6 brackets between all the coordinate functions, and well, 5 of them look log canonical, right? They look very simple. But there is one of them which is not log canonical. The Poisson bracket of A and D is given to 2BC. And then we also have a nice Casimir function, which is just a determinant of the matrix X. So what are these nice coordinate systems in this example that we were talking about? So I can find 2 of them. I just showed them explicitly. Here's one, which is A, B, C, and delta. And there is another which is D, B, C, and delta, right? So you can easily see that both of them have this nice log canonical properties just because of the brackets that you see and because of the fact that delta is a Casimir. And these 2 systems are related by, well, the simplest possible birational transformations that you can think of. Well, it's just a formula for 2x2 determinant rewritten in such a way that there are no minus signs. All right, so here in this example, our goal is accomplished. We have 2 such coordinate systems. We can restore all the generators of the ring of regular functions using these 2 systems, and they are related by a nice binomial actual transformation. Now, as you can see, I also have drawn 2 directed graphs on both sides, which we will soon just start calling quivers. And well, at this point, you can just view them as a mnemonic device. So what the quiver on the left means is that, well, it tells me what should I write in the right-hand side of my formula, right? So I want to change coordinate functions A to coordinate function D. And I know that there is a binomial formula for that, and I need to remember, well, which coordinates enter the first monomial in my binomial formula and which enter the second. And so these arrows tell me how to do that, because there is only one arrow pointing from A and that points to delta. So this will be my first term. And there are two arrows pointing towards A. And so I consider product of variables sitting in those arrows. And that is how I remember my transformations. Then, for reasons that will be explained later, I have to redraw my picture, redraw my quiver. So A becomes D. The rest of them, of this vertices become, stays the same, but also something happens to the arrow, and we will discuss this later in more detail. And so what I claim is that this simple example, gives us, so this is cloud for me to remember to write something in it. So it gives me, what it gives me is a cluster structure on GL2, which is compatible with the corresponding Poisson bracket, and it is also regular and complete. Okay, so again, compatible means that for both of these coordinate systems, Poisson bracket looks very simple, the way that I described before. Regular means that all coordinates, all functions that we see are regular functions, and complete means that I can restore all the generators of the ring of regular functions by using these two coordinate chairs. Okay, so any questions? So you please feel free to interrupt me if you have. So
maybe one naive question. So up to now, the fact that GL2 is some kind of Poisson group, it doesn't play any role, right? You have those Poisson brackets. No multiplication of GL2 is used or invoked.
Exactly. Yeah.
Mm-hmm. Okay.
This is true, but so the fact that GL2 is a group and it is a Poissonly group may help you to figure out what coordinates to choose. And and I will try to address this later.
Okay. But just to summarize, up to now, we have some God-given Poisson-Lie or whatever Poisson brackets which look nice. But maybe not completely nice, and then you find better coordinates that in this SL2 or GL2 example.
Exactly.
Mm-hmm.
Right.
Okay.
Okay, so let's just discuss the ingredients of what we just saw in this very simple example. So there are ingredients on the Poisson side and on the cluster algebra side, because at some point I'll have to talk about cluster algebras. So so again, we have this Poisson variety. Let's be a little bit more explicit about it. So it is n plus m dimensional, and it will be useful to have a torus action C star to the m acting on this Poisson variety, and we have a Poisson bracket. So first things that I need to find, and there is no prescribed way to do it, but sometimes you get lucky, is this first instance of a nice coordinate chart. And so it have to contain n plus m functions. Some of them are in blue. They're gonna be called soon frozen variables. But the Poisson bracket is again described the way I described before. It's very simple, right? Product of two functions times a constant. All right. On the cluster algebra side, we're going to define what was called by Fomin and Zelevinsky initial seed. So there is this collection of functions, this fat x, and there is a quiver. So this is not the most general definition of cluster structure, but it will suffice for us today. So how do I find this quiver? This quiver is going to tell us how to transform from one coordinate chart to another. And I claim, so this quiver has certain properties. It is not supposed to contain loops or directed two cycles. And it is intimately related to our Poisson structure. How it is related is just through this very simple linear algebra conditions that we discovered with Misha and Oleg, namely, if I consider the adjacency matrix of the quiver. So this is just a matrix which tells me signed number of arrows between any two vertices, right? So vertices of my quiver will be numbered from 1 to m plus n. So I do not consider arrows between the vertices corresponding to blue variables. So let's forget about those. So this adjacency matrix is rectangular. And so the condition is if I multiply the adjacency matrix of the quiver by the matrix of Poisson, of constants, structure constants of Poisson brackets, then I'll get something that looks very simple. I get multiple of identity and then just zeros, right? So this corresponds.
Wait, Misha, just a second. So you say BQ is n by n plus m.
Right.
And omega is what? Logically n plus m by n plus m.
Exactly, yes.
So then you say the product is proportional to the unit matrix, but it's rectangular.
No, but it's unit matrix, and then there is zeros extended by.
Okay. So it's a unit matrix. The square part is unit, and then what remains is zero.
Exactly right.
Okay.
And well, as everyone would understand, this will not define my BQ or Q uniquely, but this is where toric action will actually come handy. But I will talk about this a second later. Right. So in any case, here's a correspondence. So I had my coordinate chart with corresponding Poisson brackets, and on the other side, I have the same collection of functions with a quiver. We also will require that our functions are homogeneous under this C star to the M action. Okay, so now I want to move from one such chart to another, and the way I do it, I will just change one function at a time. So I pick one index from 1 to n. So remember this frozen ones, so they will be called frozen because, or stable, we're not going to touch them. Well, they have important role to play. So I will remove one of the functions in my coordinate system and replace it with another one in such a way that I still have the same nice property for the Poisson bracket. The structure constants will change, but the shape, so to say, of the Poisson bracket will remain the same. And how does this transformation looks like? And for this, we have to look on the right-hand side. And this is, as I described before, quiver tells me how to transform my coordinates. So I will take the one function that I want to replace, multiplied by the one I want to replace it with. And this is equal to a binomial in variables that in other variables that I have. And so I take product of all the variables that correspond to vertices in the quiver that point to my selected vertex K, plus product of all the variables to which this selected vertex K points, right? So that's a transformation. And well, in our simple example before, this was simply formula for the 2x2 determinants, and later I will list, well, many instances of such kinds of relations that, well, are scattered through math and, well, known to everyone. All right, so this is our change of variables, but then I also want this new variable to be homogeneous under C star M action, right? So this is another condition. And the claim is that if I require also that all such transformations will produce a homogeneous variable, then this relation BQ times omega equals lambda 1, 0 with homogeneity added to it defines quiver uniquely up to multiplication by a constant. So there is this nice correspondence on the left-hand side and the right-hand side. Okay.
Sorry, what about omega tilde?
Omega tilde can be just computed because you change variables, your Poisson bracket changes, and you can just see what it.
But in general, is omega uniquely determined by the quiver?
Omega is That's a
And
good question. It's not uniquely determined, but well, the set of all such omegas can be described, and roughly speaking, it is determined up to a Poisson brackets between frozen variables. Those can be changed essentially arbitrarily. So there is a moduli space of such Poisson brackets, but for all cluster business, it's not really important because the properties of each of them will be well equivalent.
Oh, okay, thank you.
All right, and so, but okay, so on the right hand side, we are going to continue with you know, notions of general definition of cluster algebras. But since we're talking about cluster structure on V, we also want more. We want new functions to be also regular on our variety, and this is not guaranteed at all because my exchange relation, simple as it is a Laurent polynomial expression, right? X k tilde is a Laurent polynomial in all the previous x's, so nothing guarantees in principle that the result will be still a regular function, but all our examples will be constructed in such a way that it is, well, more or less automatic. So we want the result in, so this is what we call regularity. We want all the functions obtained this way to be regular, right? And when I say all the functions obtained this way, what it means that I can apply the same transformations into a new seed because I obtain new collection of functions, new quiver. I can repeat this process over and over again. And one more thing that we want, and this is usually not so easy to establish, is completeness. And what I mean there is that any element in my ring of regular functions, I want it to be a Laurent polynomial in terms of any of these coordinate charts. And also, in addition, I want it to be polynomial in terms of frozen variables, but that, well, some people relax this condition, okay? So in cluster algebra language, this means that ring of regular functions is naturally isomorphic to so-called upper cluster algebras, but it is essentially equivalent to what's written on the left.
So we can skip your scary words if you want.
Right, exactly, yes.
Okay.
I encourage you to do so, yeah.
Okay, thank you.
Yeah, so that's exactly what it means. So in any of these charts, I can express any regular functions as a Laurent polynomial. That's all we mean. Okay, so that's what we mean when we say there is a cluster structures in V, and it is compatible with a given Poisson bracket. So we'll need more examples of that, but unfortunately there is one more thing that I have to describe because I kind of explicitly told you what happens to the quiver, but in fact there is a combinatorial way to describe it. So let me just do that. So many of you, I'm sure, have seen this before, but let me do it again on an example. I just want to give you an example. So here's maybe a piece of a quiver, and I want to mutate this quiver at vertex k. So this is what happens when I change my Poisson bracket, what happens to the quiver. And so there are several steps here. So first step, as you can see, I added some green arrows. So where do I add them? So whenever I have a directed path that goes, of length 2 that goes through k, I will add a shortcut. So I added shortcut from m to I, and I added 2 shortcuts from m to L, and also a shortcut from m to J. So added 1, 2, 3, 4 green arrows. And then I remembered that I told you that I do not allow in my quivers directed 2 cycles. So you see these red crosses, I remembered about that, and I crossed them out, right? And the last step, I changed the direction of all the arrows which are incident to my selected vertex k. And so these 3 steps together, adding arrows, removing cycles, and reversing directions of arrows incident to k, will produce my quiver mutation.
Except that, Misha, I believe that between J and M arrow must be in opposite direction.
And you are absolutely right.
Um,
Yeah.
Misha, may I also add some very, very small piece of criticism?
Sure.
So, at some point, kind of some of the cluster speakers at this point, they show an app where you can you can push on a button and all the arrows, they beautifully rearrange themselves, right?
Yes. Yeah.
But
And
of course, it's much more pedagogical what you are doing.
yeah,
But
yeah. Okay. Well,
but
I did want to use the map, but I don't.
are there many apps, or there is just one that everybody is
No,
using?
there are several. There is a package in Sage, I believe, developed by Greg Musiker and Salvatore Stella and others, where you can do this. And some people just do it,
Mhm.
well, in the house for themselves. But of course, the app by Bernard Keller is just indispensable tool, because this picture's good, but when you have well,
Mhm.
70 vertices, even 7 vertices is hard, but when you have 70, then it's impossible. Right?
So when you do it industrially, you should use an app.
Exactly, yes.
Okay.
But we just, so this is what we need for now. And today I'm not going to mutate too many things. So that's just an explanation of what happens to the query. All right. Okay, so let's consider another example. So our previous example was too simple. So let's consider another example. And this is one of many realizations of cluster algebras of finite type A(n-1). So cluster algebras of finite type are cluster algebras where after you do all these mutations, you only get finitely many different functions. And then this cluster algebras or these types are in one-to-one correspondence with finite Dynkin diagrams, but we'll just concentrate on the type A(n-1). And typically, when this kind of cluster algebra is mentioned, you start hearing about triangulations of n-gons, but I want a very concrete matrix realization, and this is due to Young and Zelevinsky, who did it also in other types. But again, it's easier to show it for the case A(n-1). So let's consider now group GLN. It also has the standard Poisson-Lie bracket, and again, it's easy to describe. You remember I had explicit brackets for GL2, and the easiest way to describe the standard Poisson-Lie bracket for GLN is just to say, take any 2x2 submatrix in an element of GLN and write exactly the brackets that I've shown you before, and this is what it is, right? But this has many Poisson submanifolds, and important Poisson submanifold of so-called double Brouillard cells. So I'm going to select one of them. I'm not going to go into what they are. Many of you know, but there is an explicit realization here. I'll just say for the experts that this is Coxeter double Brouillard cell corresponding to the following Coxeter element in the symmetric group. But you can also simply describe it by a set of tri-diagonal matrices, which have non-zero determinant and non-zero off-diagonal entries, right? And well, this is a very nice and important object. There are various integrable systems like Toda lattices that live on such things, and well, there are many other applications, orthogonal polynomials and such. And now I'm just going to claim, again, without saying how, that you can select a nice initial set of coordinates that will enjoy these properties of being compatible, have a low canonical Poisson brackets. And what's hidden here is that you can select it in particular if you know how to factorize this matrix X into simple pieces. But for us today, we'll just need to know what it is. So, well, what you do, you just take trailing dense principal minors of X, right? So you just start with, well, phi n will be just Bn, and then phi n-1 will be 2x2 principal determinants in the lower right corner, and so on. And my claim is that they have nice Poisson brackets. Together with these off-diagonal entries, they will form coordinate system of the type we like. Determinant, of course, will still be a Casimir. And when you compute according to the rules that I described before our quiver, this is how it will look. So I'll just, it looks very simple, like it looks like Christmas trees that you forgot to, well, throw away, and now this is how it will look in June, right? So this is our quiver. And cluster transformations done the way I described before, but in fact, when you try to compute this cluster transformations, you realize that what you are using is just the Dennanot-Jacobi identities for minors. So this classical identity for minors of an n by n matrix. And this is the reason why you get a regular function, because all these identities have a shape. Product of two minors is equal to sum of two products of two minors. And so when you divide by something, you still get a polynomial function, right? And this is kind of a typical situation. So in other instances, in other examples, you use, so essentially for all geometric examples of cluster algebras, you use something of this sort. So it could be short Fluker relation, it could be Whitehead move for Teichmüller series, it should be just Ptolemy relations. You can add Hirota bilinear relations. So all of them are of this sort, and all of them are essentially glorified version of the formula for 2x2 determinant. So sometimes you have to generalize it, like Fomin and Zelevinsky did for double Brea cells in other types, but this is kind of a typical modeling relation for cluster algebras of geometric type. Okay, and so I told you that this is a cluster algebra of finite types, which means that there is finitely many, just finitely many different cluster variables. And in fact, Young and Zelevinsky proved that the set of all possible cluster variables is, well, except for the frozen ones, so frozen ones we never touch, is precisely the set of all possible dense principal minors of our matrix X. Okay, so this is another example, one of many. So at this point, I could go into arbitrary Poisson, simple Poisson-Lie groups, or Grassmannians, or Teichmüller spaces to produce, to show other examples of this regular complete cluster structures. But instead, I want to go back to GL2 and present an example where something goes wrong, but not so wrong that we cannot correct it, okay? Because we need to get to generalized cluster structures, and we need the reason to do this. But again, if there are any questions, please let me know.
Misha, sorry, which Whitehead move?
So when you have you have a Riemann surface with a hyperbolic metric, and you have an ideal triangulation of the surface, and when you flip rectangles, flip diagonals and rectangles in this triangulation, something happens to the lengths of well, to carefully adjusted lengths of arcs in this geodesic in this geodesic triangulation. So that's that kind of Whitehead move. But it's the same relation like for Ptolemy relation for quadrilateral inscribed into a circle, right? So it's product of lengths of diagonals is equal to sum of products of opposite sides. Okay?
Thank you.
Okay, so here's another example. So we're going to get towards Drinfeld double of GLN. Again, I don't want to go deep into a series of Poisson-Lie groups, but as a set, right, or as a space, it's just a direct product of GLN with itself, but it can be also written as a product of standard Poisson-Lie group G, which is sent there through diagonal embedding, right? So instead of pair of, say, elements X, Y, we have here X, X, and what's called dual Poisson-Lie group G star, which is made out of pairs upper triangular and lower triangular matrix with matching diagonals. All right, so this is itself a Poisson-Lie group. So you can write our matrix for it, or you describe it using Manning triples. But again, for us today, it's just important that it has a Poisson bracket, which is quadratic in terms of matrix entries of pair of elements X, Y in GLN. And well, it is not log canonical at all. But if you try hard, you can find a nice log canonical coordinates. And one such choice is presented here. So suppose I just happened upon this collection of functions, and I can compute a quiver, and I will obtain what looks like a nice quiver, nice initial seed, right? So there are some matrix entries, there are determinants, which are still Casimirs, and there is a strange functions, which is like a mixed determinant. And you would notice that the strange function is not in a circle, but in a hexagon, and the reason for that is that it behaves differently. So I'm following the same recipe, but if I try to apply cluster transformations that was described before to this variable, I will not get a regular function.
Sorry, just a stupid question. Don't you need 8 of them?
This is an excellent question, right? And you will see the answers the answer right away.
Okay.
Right. So there is one more Casimir here. So for Drinfeld double, if you just take, so let me just write it here. If you take a characteristic polynomial, let's say of this form, lambda x plus mu y, and expand it, so it will be some functions times lambda I mu n minus I. All of these CIs will be Casimirs, right? So in my particular example, there is determinant of x will be one of this coefficient, determinant of y, but there is one more, which is of such a nature that it just doesn't fit in my quiver in any way. But also, as I said, if you just apply cluster transformation to this hexagonal vertex, you will not get something which is polynomial. And we want something polynomial. All right. So yeah, so this is but, right, that I have here. It doesn't work, but we can adjust our cluster transformation, right? But the price that we'll have to pay is that it's no longer binomial on the right-hand side. So I'll just write explicitly what this is. So instead of considering just a relation product of all times nu is equal sum of two monomials, now I have product of all times nu, and this is how it will be computed. It's nice and polynomial, but it will be sum of three monomials. And so it's a more complicated transformation, but in this transformation, you do see this missing ninth variable present, okay? And this is an example of generalized cluster transformation. So example of usual cluster transformation was formula for 2x2 determinants, and this is some strange identity, but it still works. And this is what is a generalized cluster transformation. And once you adjust it, definition of cluster transformation in this hexagonal vertex this way, everything else works. So you will have.
Sorry, just a stupid question. Should I think of this CXY as
right.
another frozen variable, sort of?
Right. You can. Well, so we have trouble actually with terminology there. It is frozen variable, but it is a different kind of frozen variable. So we'll call it isolated frozen variables. It does not belong to a quiver. And later I will show you a formalism which tells you how to deal with them. But it is certainly frozen.
Okay.
Yeah, we're not going to change. Right, but once you adjusted definition of cluster transformation, of course you'll have then to adjust also our expectations of what to do with the quiver, and I will discuss it a bit later. But then everything else works. So you'll have regularity, you'll have completeness, everything will be fine. And this particular picture will produce a generalized cluster algebra, but also a finite type. Here it will be a finite type B2, but
Could I ask you a question?
B3, sorry, B3, yes.
What is the new variable in the equation that you've written?
This is, right, so you see this, I wrote this expression in two different ways, right? You can write it as a determinant of this y22 times x plus x22 times y, right? So it's determinant of 2 by 2 matrix, right? You can expand it in terms of variables y22 and x22, and being a determinant of 2 by 2, it will produce 3 terms rather than 2. So the coefficient of the middle term of the term y22 times x22 is exactly cx1.
And you're thinking of that as being the new variable, not the thing on the left-hand side?
No. This is an additional frozen variable.
I understand.
A new variable, and a new variable is this purple thing on the left-hand side.
Okay, but I thought that, oh, I see. But that's regular. Okay.
Yeah, that is regular, yes. Okay,
thanks.
all right, so how does it look? Same Drinfeld double, but n arbitrary. Well, n arbitrary means n is going to be 4, right? Because otherwise it will not fit. So let's look at the pictures. This I had to to copy from somewhere. This is actually this is a snapshot of Bernard Keller's applet, actually, right? So it does appear here, right? And this looks strange, but I will try to explain. So here is a collection of nice functions that form this log canonical system for the case of double of GLN. And let me just maybe explain what this, at least some of these functions are. So these yellow guys are certain nines in dense minors of X. Remember, we had the pair of entry elements X and Y, and the blue guys are different kinds, but the nice dense minors of Y, and the red guys are this kind of mixed determinants, mixed minors, as in the previous example. And the gray guys, it will require more time to explain what they are. So let me just say that they're going to be funny looking, but they are all polynomial functions. And there is, let's call these functions, all of them phi, attached to different vertices. And there is only one variables that will be transformed here in a generalized way, and this is how this generalized way looks like. So again, it's a old one times new one is equal to determinant of this, you can say, matrix pencil. And when you expand it in terms of phi2, phi3, coefficients will be, of course, the very same Casimirs on the doubles that we described before. And so if you carefully count now vertices in this picture, you will also find out that, there is not enough of them. And the reason for that is, so we need to have here what this is GL4. So we have to have 32 of them, and you only see 28. And that's because there are all these extra Casimirs that I didn't show in the picture. All right. But again, you have nice properties, regular, complete, generalized cluster structure. In fact, in this picture, there are many different cluster structures contained. So let me just list them. So, let me just make it a little.
Can you explain? So is this picture, the example that you drew there, is that the double Bruja for GL4?
No. This is double of GL4. It's Drinfeld double of GL4, right? So it's GL4 cross GL4 with a Poisson bracket coming with respect to the Poisson bracket on the double.
And each vertex should have 3 outgoing edges?
Not necessarily. Well, so some of them have 6, as you can see now. That's well, the quiver is computed according to the same recipe as before. I somehow found this nice coordinate system. I found matrix of Poisson bracket. I inverted it like before, and this is the quiver it gives me. If I were to pick a different collection of log canonical coordinates, this quiver will look very different. So it doesn't have, it's not like a situation with direct Postnikov's networks where it has to be trivalent. So here, actually, if you start mutating, you will soon have valency of, well, of thousands, because this is not a finite time. But yeah.
And
Sorry.
Yeah.
yes, Misha.
One more question. But how is it? So this is a coordinate system also on some dense chart, right? In the double, or is it?
Right. So it's always, so yeah, it is coordinate system on some dense chart. In all of the examples, it is on a dense chart.
Okay.
Yeah, but I claim that this picture actually contains several nice cluster structures. So, well, first of all, the ones that we build it for, it's regular, complete, generalized cluster structure on the double. But if I restrict all these functions to just diagonal embedding x equal to y, that will kill everything in between. So we'll have just yellow and blue, and some of yellow and blue will be identified. Then it will be precisely the regular complete cluster structure on GLN, the same ones that can be obtained through analysis by Bernstein, Fomin, and Zelevinsky. And if you, on the contrary, restrict to the dual Poisson-Lie group, so that will be this gray and red stuff, and that will give you regular complete generalized cluster structure on GLN star. And you can also, in the same picture, find conjugacy, well, cluster structure on generalized cluster structure on conjugacy class in GLN intersection with B plus B minus, or if you just look at this gray triangle, you'll get similar generalized cluster structure on B plus W0 with respect to this dual Poisson-Lie bracket. So this is, in a sense, very nice universal, well, not universal, but well, useful picture, I would say, right? So a lot of stuff is contained. Now, what about this generalized cluster transformation, this one? So where does it come from? So I claim that this is an instance of, well, it plays the same role that the Plücker relation or the Jacobi relation played for the usual cluster structure. So there is what we can call a master identity, but I put it in quotation marks so it doesn't sound so self-important, but there is an identity which, at least for us, was present in all examples that we were able to consider. So I don't know if I want to talk a lot about this. This is just a matrix identity, right? Which I can, which I can try to show, right? And this is how it looks. So without going into gory details, you take just the matrix and a couple of vectors. You construct some polynomial, well, of this matrix using the cyclic matrices, and you can find then this identity, which is of the kind that we want, because well, I switch right and left here, but the left-hand side has obviously n+1 terms, and the right-hand side is a product of two functions which are polynomial in matrix entry. So all the identities that we saw before.
Misha, I think you're pressing a key on your keyboard or something. We're hearing, now it's gone.
Sorry, yeah. So all identities that we saw before, this generalized identities, are of this shape. All right. So now that you have master identities, like, well, now we have a hammer and we have to go looking for nails to hammer in using it. So other examples of generalized cluster structure where something like this can be used. Well, unfortunately, I came to a point where I have to give you more details about how these generalized cluster structures work, and then I'll probably run out of time. But I've been neglecting to tell you how you actually properly modify definition of cluster mutations. So, so what is a general setup now for generalized cluster structures? Because now we'll have to deal with it. This is our modification of a definition given by Leonid Chekhov and Misha Shapiro, where these coefficients that were called CI previously, this coefficients in this expansion, they were constant, but now for us they're not constant; they're also functions. So, what is the modification? So now, in our quiver, for each non-frozen vertex, we assign a multiplicity, right? That's just a positive integer di, one or more. So one would be normal situation, and also a string of coefficients. So this hidden frozen variables now will be encoded in the string of coefficients. So the strings of length di plus 1, as you can see. And our generalized exchange relation becomes more cumbersome, but it's cooked out of the same ingredients essentially, right? So again, old times new is equal to, it's no longer binomial. So this multiplicity tells me the length of the relation. The relation will be of length dk plus 1. Coefficients just plays the role of coefficients, but then instead of this nicely defined just product over arrows pointing towards vertex, product over arrows pointing away from vertex, we have a few more ingredients. So I still have this product, but of mutable, not frozen verticals, over mutable vertices, not frozen ones, which is presented here and here, right, for pointing away and pointing in. But then I also have these strange objects which are made out of, you know, honest to goodness frozen variables. And okay, so this is how they look like. I have to take product over all frozen variables and then take a number of arrows pointing from my selected vertex k to each of these frozen variables, multiply it by r and divide by the multiplicity, and then take the floor functions out of that. And it looks weird and unpleasant, but this is a definition that works. So, but long story short, we have a long, well, you know, carefully defined longer relation. And
Misha, in the end, is it going to be a polynomial, or those denominators will stay?
So it's going to be in our examples, based on this master identities, it is going to be a polynomial.
Okay, but in general, it's not known. Or
In general, well, but in general, even for normal cluster structure, you will generally get Laurent polynomial rather.
No, but I mean like integer. Okay, maybe.
Here, no, here it's going to be, yeah, it's going to be a polynomial. Yeah, sorry.
So the powers in the end will have no fractions.
Yeah, exactly.
No, there's a floor. There's a floor function.
This is why the floor.
Okay.
Yeah. All right. Yeah. All right. And then, yeah, so this is our exchange relation, and coefficients will also have to mutate, but in a very simple way. They'll just switch order. And quiver mutation will have to be modified too. And essentially, all you have to do is, in some situations, instead of adding shortcuts as a single arrow, you add, well, so for example, in this example that I see, between I and J, normally I would put just one arrow, but here I have to put dk arrows, where dk is now multiplicity of this vertex at which I do a mutation. Okay, so this is not such a drastic change. And the claim is that under these definitions, all nice properties of normal cluster algebras will remain intact. So, and this is due to Chekhov-Shapiro, Rupel-Nakanishi, and Nakanishi, and in our work. So all nice properties, meaning Laurent phenomenon, if there is periodicity, there will be dialog identities. So all of that will work. All right, so that's the definitions. Sorry, I had to, kind of run over it, but it brings me to the next family of examples. And that is the situation where you just have some nice matrix construction and can apply it to many instances of generalized cluster structures. So let's now consider so-called periodic staircase matrices. So I have an infinite matrix, just block toplets matrix made out of two n by n matrices of special form. So special form, well, is described in this example. I will call inner diagonals. So what are inner diagonals? So if I have a diagonal in this infinite periodic matrix, and I view it as a main diagonal, right? Because it's infinite, I can do it in many ways. But if I view it as a main diagonal, it does not decompose, right? So again, we have this periodic matrices with n by n blocks with k inner diagonals. Okay, and so I'm going to build generalized cluster relations from any such periodic matrix. So the idea is the following. Well, we have this blocks, block rows. From each block row, I will remove the first row, and when I do this, my matrix just collapses a little and it's no longer irreducible. So in this collapsed situation, I will select the maximal irreducible component, let's call it phi of L, and it will be of some large size, which is roughly equal to k times n. So k is number of inner diagonals and n is a size of the block. All right, so now that I have something reduced, so just finite matrix, then I can again define this trailing principal minors of this matrix phi, and I can also define analog of what we saw before of this generalized characteristic polynomial, which will be in this case of a degree k, right? The k is number of inner diagonals. So, well, you can view the situation as linear polynomial acting on infinite sequence of vectors, and then you just do the usual spectral theory, and this is where such objects appear. And whenever I have such a situation, I again will have this generalized relation where the largest of functions that I just defined multiplied by some other function, which is also polynomial, will be the sum of lengths k plus 1 with coefficients which serve as coefficients of a characteristic polynomial. And then the only things involved there are other functions that naturally present in the picture. So functions that I defined before, this fees, and also, well, this was not necessarily present of the picture, but it's not so complicated, right? I have this block B, I take some minor of this block, and that's all right. So it looks something that belongs in some sort of cluster, generalized cluster structure. So now one just need, sorry.
And this phi 1 star, is it also some natural minor of something, or
not always, right? It looks, yeah, it looks less natural, but it works. So when number of inner diagonals is 1, then it is. But otherwise, it's more complicated. But it is polynomial, and you can continue the process, right? And so once you have this identity, the natural question is whether or not you can use it as a generalized cluster transformation. And of course, I wouldn't be telling you this if the answer wasn't yes. Okay, and in the remaining, what do I have? 1 minute? I can.
Let's negotiate. How much do you need reasonably?
Reasonably, I think I can. Well, between 5 at most 10, I should finish.
10, let's say 5.
5 is good. Yeah. All right. I'll finish soon. Right. Let's go back to, well, let's consider several examples, right? So let's go back to our Drinfeld double, right? So previously I presented, or at least, well, pretended to present initial seed for generalized cluster structure on the double. And here is a different construction of initial seed for the same Poisson, compatible with the same Poisson structure. So in this case, in my periodic matrix, A is simply equal to X, B is simply equal to Y. Number of inner diagonals, if you just draw it, you will see is equal to N. And after I do this contraction of a matrix, I will get something of size N times N minus 1, which will, again, will be block toplets, but with rectangular blocks. And I can define these functions phi as I defined before. And then I have a theorem that if I take these functions phi, and then I take some nice dense, again, minors of X and Y, which are listed here, then this will be a nice initial cluster for regular, complete generalized cluster structures on double of GLN. And I can present you a quiver. As you can see, there is only one, again, only one generalized vertex. So quiver looks not so scary, but, well, not so simple either. So this is just a claim. So that there is a complete regular generalized cluster structure with this initial seed. Okay, and it is compatible with the standard Poisson structure, but because you'll be justified asking me, how does this compare with my previous generalized cluster structure? And interesting thing is that for n equals 4 and conjectural for any n greater than 4, this cluster structure is actually different from the one that we discussed before. They're not equivalent. They cannot be transferred one to another using cluster transformation. So this is an example. I think Sean Keel was asking for such an example before. Natural geometric example of two non-equivalent cluster structures compatible with the same Poisson bracket with the same frozen variables. There is a conjecture that it can be embedded into larger normal cluster structure, and then they become equivalent, but that's under consideration. And then here's another example. So now let's consider periodic band matrices. Periodic band matrices, well, again, important presence in theory of integrable systems, again, like Toda lattices in the generalization. So in this case, so we consider n periodic infinite matrices with k+1 bands, and I've shown how you can break it into the square blocks A and B. And then when you collapse the matrix L by removing the first row everywhere, you'll get the size of it equal n-1 k-1. What is a Poisson bracket here? Well, Poisson bracket here is obtained this way. You can view this as a Poisson submanifold in loops in GLN with respect to trigonometric R matrix bracket. Just consider this linear loops, reduce this to A's and B's of the form above, and then this is a Poisson bracket that we are dealing with. It was recently also employed by Anton Zosimov in study of pentagram maps, and we have a similar result. If you just consider all these functions phi together with a quiver that is depicted here, again, it looks a little busy, but it's nice and regular, then you get regular complete generalized cluster structure compatible with this natural Poisson bracket on band periodic matrices. And maybe I'll just finish with one more example, because I wanted to go back to example we discussed before due to Young-Zelevinsky. So there we talked about finite tridiagonal matrices, and now the simplest case of this band periodic is this just periodic tridiagonal matrices. And in this case, generalized cluster structure will be of finite type, but not an-1, of finite type Cn. And again, we can describe all cluster variables because it's a finite type, and this is just distinct dense principal minors of this tridiagonal periodic matrices. And the quiver, if you remember how it looked before, so well, become a little bit again heavier, but the old quiver of the previously considered quiver of Jan Zolovinsky would be right here, right? Okay, and I just want to mention also that the same type of cluster structure appeared in monoidal categorification of monoidal categorification of the same type of generalized cluster structure was considered by Gleitz in the study of representations of UQSL2 hat at roots of unity, and there are indications that her results can be extended to using the constructions that I presented to SLK instead of SL2. All right, so there was one more example, but I honestly wrote here time permitting, and time obviously does not permit, so I will say thank you and congratulations again, Anton.
Well, thanks a lot. Well, thank you very much. Any questions or comments? Yeah, you can just unmute yourself and ask questions or raise hands or whatever.
Misha, when were these generalized cluster transformations discovered?
Well, they were implicitly, so we implicitly discovered them in our book, but then, imposed a lot of unnatural conditions in the hindsight to get rid of them, right? But then, so Misha Shapiro and Leonid have rediscovered them with constant coefficient in a study of cluster algebras coming from surfaces when you have orbifold points.
I see.
So,
and these are also, are they also are there also quantizations or non-commutative versions of the generalized ones?
Yes, there are. So several people worked on them, in particular Tomoki Nakanishi. And my first example for double of GL2 actually appeared, I think, in quantum situation in the work of Bernstein and Greenstein. So there are natural quantizations of those as well. Yes.
I see. Okay, thanks.
More questions?
Maybe one other question. Have you ever encountered, either in the generalized or the usual cluster, people who consider like a Kähler metric on a cluster variety?
So I can't say right away, but certainly there were cluster structures and varieties that support Kähler structures. So yeah, so I would have to think about it. Sorry.
Okay.
More questions? I have one more question. How is it in the beginning you explained that if you have an ordinary cluster structure, then basically you can classify all compatible Poisson brackets, and you just add log canonical brackets between frozen variables, and that gives the whole description.
Right.
Now, what about, is there a similar statement for those generalized structures? And if yes, how does it, because now you have different types of frozen variables. What's the, and even what's, maybe to start with, what are the conditions, right? Before you said that the condition is that the brackets should be log canonical in all charts.
Right.
And also all variables should have definite weight under the torus actions. Now, is there like, there was a kind of whole package in what you said in the beginning, and then of course I was a little bit waiting for a similar package
Oh, it is. So sorry, I should have emphasized. So there is a similar package. Right?
Right.
So one nice geometric way to describe all the structures is so you fix one of this Poisson structure, right? And then you have this toric action defined actually by Hamiltonian flows of this usual frozen variables. And if you also endow this torus with log canonical Poisson structure of any kind at all, then you can transform them all one into another.
For ordinary ones.
Yeah, ordinary.
And then for those new ones, what about the new frozen variables?
So their ratios are K-ziggers, so they'll just stay the same.
Oh, they all have vanishing Poisson brackets with everything.
Right. Yeah, right.
Okay, so you say basically there is a similar classification.
Right, exactly. Yes.
Mm-hmm. Okay. Well, are there any more questions or comments? Well, if not, Misha, thanks again.
Thank you.
And thank you for a beautiful picture. Next time we'll have Camille Laurent-Jangou, who will be speaking about singular foliations. So in 1 week from now on Global Poisson. Well, so thank you again, and see you next week. Bye-bye.
Bye-bye.
Right.